In this last video, let's explore. So we have this constant function connected to a quadratic function. We just connected it to a linear function. So I'm going to try and connect this one to another quadratic function so that I can use that hill feature in order to be able to bring it back down again. And this will be the highest point on my roller coaster. So looking at my other function that I just completed, that point that I have right here is the point 3, 8. So I know that I need to connect a function to the point 3, 8. So that's why I have that here on my paper, 3, 8. Now, this point you can put wherever you want. I don't know how high or low it needs to be because that's going to depend on making it differentiable first. And as soon as I make it differentiable, then I can go back to making it continuous again. This x value, however, you can decide. All I know is that it needs to be to the left of 3, but you can decide wherever you want that vertex to be. So if you want it to be at 4, put 4. If you want it to be at 5, put 5. If you want it to be at 3.5, you can put 3.5. I just chose 4 randomly. So I set up my equation. I said, okay, I have this linear function that's over here. This is the one we just made in that last video. I have a linear function that's first. That's 2 times x minus 1 plus 4. That's this function right here. All right, we put the domain to be 1 to 3. Now, notice that I have a lot of variables in this equation. So that's going to happen as you guys go through. I don't know what my stretch factor should be, so I have an a that's left there. I chose 4 randomly. Remember I told you that I just randomly chose 4 out of thin air, and that's why I decided to make this 4. You could have chosen 5 or 6 or 7 or whatever you wanted. I know it's a quadratic, so that's how I know that the function should look like this. And my b value, again, I will not know what I should make b. I will not know what I should make bb until after I find out what value of a makes it continuous. So, what value of a makes it differentiable. So first things first is at this breaking point at 3, this function needs to be differentiable with this function. So they need to have the same derivatives in order to make this a nice smooth connection. So the first thing I want to do is take the derivative of both of them. And again, notice that I have these variables left in them, and I'm not going to know what my k value is, or my b value in this case. So I'm gonna have to leave that b for a while, and I'm not going to know what a is until after I do this next step. So let's take the derivative of both of these. The derivative of 2x minus 1 plus 4, if I distributed the 2, it's just a linear function, so the derivative of that is just 2. The derivative of this quadratic function, I would require the chain rule. So if I bring the 2 down front, I have 2a times x minus 4 to the first power. The derivative of the inside is just 1, and then b, the derivative would be 0 since that's a constant. So that's 2a times x minus 4 to the first power. So I'm going to force these functions to be differentiable at the breaking point of 3. In order to do that, I plug 3 into both functions for x. So if I plug 3 into the first function, I get 2. Notice that I'm setting it equal to the second function because I'm trying to force it. I want to know what a is that's going to force these to be differentiable. So if I plug 3 into the second function, I get 3 minus 4, which is negative 1. 2 times negative 1, which is negative 2. And if I divide that on both sides, I get that a should be negative 1. From there, if I come back up here to the top again, I know that my a value is negative 1. In order to force these to be differentiable and continuous, so I already know that a should be negative 1 in order to make them differentiable. Now, in order to force them to be continuous, and I'll kind of write this as we go, if I come back up here again, and I say, okay, now instead of writing a, I'm going to write negative 1 x minus 4 squared plus b. If I need these functions to be continuous, all I need to do is plug the breaking point, which is 3, into both of these functions now and solve for b. So if I plug it into the first function, I get 2 times 3 minus 1 plus 4, and that should be equal to negative 1 times 3 minus 4 squared plus b. And now I have an equation that only has one variable in it, which will let me solve for b. So if I solve this, 3 minus 1 is 2, 2 times 2 is 4, 4 plus 4 is 8, equals 3 minus 4 is negative 1, negative 1 squared is positive 1 times negative 1 is negative 1 plus b. So therefore I know that my b value, if I add 1 to this side, my b value needs to be 9. So now I have my quadratic equation. So in order to figure out my a value and my b value, I had to go through these steps of finding the derivative in order to first force it to be differentiable. From there, we can go back and find my b value or my k value, my vertical shift, by forcing it to be continuous after I know the a value that makes it differentiable. So let's enter this as our quadratic equation. So it's going to be negative 1 times x minus 4 squared plus 9. So let's enter that into Desmos and see what we get. So we'll name this a new function. So I have b of x, c of x, d of x. We'll skip e just because I'm not a big fan of the vowel names. I'll call this one f of x. Oh, I guess g of x comes next. A, B, C, D, E, F. No, F is right. Oh, I shouldn't doubt myself. F of x equals -1 times x minus 4 squared plus 9. Pull this down just a little bit. So again, notice that we don't need it when it's less than 3. So let me restrict that domain. So I want 3 to be less than x, which is less than or equal to. And again, you can make up whatever number you want it to be less than or equal to. So I'm going to say less than or equal to 5. No, I don't like that. Less than or equal to 6. Better, less than or equal to 7. Sure, I kind of like that. So maybe I'll have it less than or equal to 7, and I'll continue a different function from there. So we have our constant function, our little mini quadratic. We have this linear function that hooks up to another quadratic, and I have to go from there. So remember, I need 5 different types of functions. So far in this graph, I have 2 different types. I have a linear function, and I have a quadratic function. We're not going to count that constant as its own function. So take off from here. If you need more advice on how to make them continuous and differentiable, please let me know.